This video concludes the six-part series on modeling benzene mass transfer from polyvinyl chloride degradation. In this conclusion video, I will discuss the information which has been covered in this short course. In the introduction video, we gave background on the importance of benzene dissolution and volatilization. Thermally degraded polyvinyl chloride leaches benzene into water. The acute and long-term health effects of exposure to benzene were discussed. Benzene is a known carcinogen. Concepts which would be covered in detail later in the video series were introduced. The organization and structure of the video series was defined. Concept 1 was the dissolution of benzene from the solid polyvinyl chloride pipe into the liquid water. A video was made which described theory, assumptions, and calculations which would be used to model the dissolution of benzene from polyvinyl chloride into water. An ordinary differential equation was found to be used in the model. A second video about Concept 1 was made, which explained how to write code in MATLAB which would model the concentration of benzene in water over time in our scenario. Concept 2 was the volatilization of benzene from water into air. The first video about Concept 2 was about relevant theory, assumptions, and calculations which would be used to model the concentration of benzene in water and air over time during volatilization. Two ordinary differential equations were found, one to show the change in concentration of benzene in air over time, and one to show the change in concentration of benzene in water over time. In the second video about Concept 2, three methods for writing code in MATLAB to model the scenario were explained and demonstrated. In this conclusion video, we will be going over what we have covered in this video series. This is a brief overview of the information which was presented in the introduction video. After the tubs and campfires, contamination was found in water within the water distribution networks, but not the source water. A 2021 study showed that contaminants were released from commonly used drinking water plastics when they were thermally damaged. Benzene was one of the contaminants detected in the leachate. There are serious acute and long-term health hazards of benzene exposure. Acute symptoms of benzene ingestion and inhalation include rapid or irregular heartbeat, convulsions, and death at very high levels. Long-term symptoms of exposure can include anemia, excessive bleeding, and cancer. The second video in this series was about the theory, assumptions, and calculations made to create an ordinary differential equation which would model the change in concentration of benzene in water over time due to dissolution from polyvinyl chloride into water. We looked at benzene leached from a thermally degraded polyvinyl chloride pipe. Polyvinyl chloride is commonly used in drinking water distribution systems and has been found to leach benzene into water when damaged by heat. When polyvinyl chloride is thermally damaged, benzene becomes a solid which dissolves into water. The concentration of benzene in water increases over time according to the mass transfer coefficient, K. The constants used in the model of dissolution of benzene from the polyvinyl chloride pipe into the water are given on this slide. Flow rate, Q, in volume per time was 0 in our model, meaning that the water in the pipe was stationary. Pipe length and pipe diameter were given values. The mass transfer coefficient, K, in 1/time units, was a constant. The saturation concentration and initial concentration of benzene in water, in mass per volume, were given constants. A single resistance model was used to find an ordinary differential equation to represent the change in concentration of benzene in water over time. The diagram shows the control volumes of water and polyvinyl chloride, the interface between them, and the concentrations across each volume. For concept 1, we considered still water in a polyvinyl chloride pipe which had been degraded. Since the water was not moving, we treated the system as a continuously stirred tank reactor. We assumed that the concentration of benzene in the water was uniform across the control volume. We created an ordinary differential equation which we used to model benzene concentration in water over time. Mass flux of benzene in water, J, was equal to K, the mass transfer coefficient, times delta C, the concentration difference of benzene in water. Delta C was equal to the difference between the saturation concentration and the concentration of benzene in water, which changed with time. Using mass balance, we reached an ordinary differential equation which showed that the change in the concentration of benzene in water over the change in time, multiplied by the control volume, was equal to the mass flux, J, times the surface area of the benzene. The surface area of the benzene was assumed to be equal to the surface area of the inside of the polyvinyl chloride pipe. The third video in this series was about writing code in MATLAB to model the change in concentration of benzene in water over time due to the dissolution of benzene from polyvinyl chloride into water. ODE 45, a built-in function in MATLAB, was used to solve the ordinary differential equation we found in the previous video. ODE 45 solves ordinary differential equations numerically. The solution which resulted from using ODE 45 was plotted as concentration of benzene in water in grams per liter versus time in seconds. The concentration approaches the saturation concentration of benzene in water according to the mass transfer coefficient K, and then plateaus at the saturation concentration. The fourth video in this series was about the theory, assumptions, and calculations made to create ordinary differential equations which model the change in concentration of benzene in water and air over time due to volatilization of benzene from water into air. This video considered mass transfer from liquid to gas phase. We thought about a volume of water with a concentration of benzene, which was placed in a container with some surface area exposed to the control volume of air. We created ordinary differential equations to represent the change in concentrations of benzene in both the liquid and the gas phases. To create ordinary differential equations which modeled the change in concentrations of benzene in water and air over time, we used Henry's law, a one-resistance model, mass flux, and mass balance. The resulting ordinary differential equation for the concentration of benzene in water was the change in concentration of benzene over the change in time times the volume of water is equal to the negative mass transfer coefficient times the exposed surface area of water times the concentration of benzene in water minus the concentration of benzene in air over Henry's rate constant. The ordinary differential equation for the concentration of benzene in air was the change of concentration of benzene in air over the change in time times the volume of air is equal to the positive mass transfer coefficient times the exposed surface area of the water times the concentration of benzene in water minus the concentration of benzene in gas over Henry's rate constant. This section will review the MATLAB techniques which were used to model the volatilization of benzene from water into air. Ordinary differential equations were solved both numerically and analytically. Euler's method was used to numerically solve the differential equations in MATLAB. The dsolve function was used to analytically solve the differential equations in MATLAB. The results of plotting the solution from each method as concentration of benzene in milligrams per liter versus time in hours are shown. Both the numerical and analytical solution show that the concentration of benzene in air increases and the concentration of benzene in water decreases over time. This is the end of the conclusion video about modeling benzene mass transfer from polyvinyl chloride into water and from water into air. Hopefully you have enjoyed this short course. There is a quiz over this conclusion video consisting of multiple choice questions about the material which was covered in this video series. These are the sources which were referenced in the creation of this video series.